back from break. How's everyone still feeling today? All right, that's what I like to hear. So we were talking about conservative work being independent of the path taken between the starting point and the ending point. And if we take the path straight up and we calculate the work done by the force due to gravity, it was simply the force due to gravity times the forward displacement up times the cosine of the angle between the force due to gravity and the forward displacement, which turned out to be 137. And we found out that the work done by the force due to gravity was equal to 100 newtons times 5 meters times cosine of 127 degrees. And when we figured that out, going straight up the ramp diagonally, we got an answer of negative 300 joules. What I want to show you, if we drag that object straight across the bottom, and then we dragged it or lifted it straight up, the work still turns out to be negative 300 joules. Watch what happens here. The work done by the force due to gravity to bring it across the bottom, I know I get carried away with these subscripts, the work sub F sub G sub bottom, as it goes across the bottom right here, it would be Fg times the displacement across times the cosine of some angle, I don't know what angle, I'm just going to call it theta 2. What's theta going to be 2? As it goes across the bottom. Remember, Fg is acting straight down, and the forward displacement now would be straight across. So what would this theta right here be as it goes across the bottom? 90 degrees. And what's the cosine of 90? 0. So how much work would the force due to gravity be doing as it slid horizontally across? Big fat 0. So this here turns out to be a 90 degrees, and that ends up making this whole thing turn out to be 0 joules. Now, what about when we lift it vertically straight up? When we lift it vertically straight up, I'll call it the work done by the force due to gravity, on the way up. Well, again, that's going to be the force due to gravity times the forward displacement times the cosine of some theta, in this case it would be theta 3. Well, the force due to gravity is still 100 newtons. That's the weight of the object. The forward displacement, careful, it's not 5 anymore because we're going straight up. And when we go straight up, what's that forward displacement? 3 meters. And then the cosine of some theta 3, if we're moving it up this way and the force due to gravity is acting in the opposite way, forward displacement up, Fg down, what's this theta 3 going to be right here? 180. Cosine of 180 is negative 1. We multiply 100 times 3 times negative 1. What do we get? Negative 300 joules. So if we add the work done across the bottom, 0, plus the work done to go straight up, 300 joules, what does it turn out to be equal to? Same thing as before. As a matter of fact, if I figured out the work done by the force due to gravity along this path, guess what the work done by the force due to gravity along that path would be? Negative 300 joules. That's what makes it conservative work. It doesn't depend on the path taken.
I would just have had the same starting and then.
Yes. Yes. So conservative work does not depend on the path from the initial point to the final point. You get the same answer regardless of the path taken. An example of this is the work done by the force due to gravity. The big news is, conservative work can be replaced potential energy formulas. This is the big news. This is what makes it simpler. So what we need to do is introduce gravitational potential energy. It's stored up energy due to altitude. Anytime an object is lifted up and has any sort of altitude, it has gravitational potential energy. In order to calculate the gravitational potential energy, you have to multiply three things together. And it always reminds me of like a little cheerleader chant. Gravitational potential energy equals the mass of the object multiplied by the acceleration due to gravity, 9.81 meters per second squared on the surface of the Earth. We normally just round to 10, times the height from some reference point, whether it be the ground, the floor, whatever we decide to be the reference. So gravitational potential energy is mgh. It reminds me of the cheerleader cheer when they go like SHS, like Syosset High School. You know the cheer? I'll try. You guys join in. Ready? MGH. Little louder now. MGH. Everybody now. MGH. You know, gravitational potential energy. So instead of calculating the work done by the force due to gravity, what we're going to do is calculate potential energies. But there's one last little trick, one last little glitch. Let's go back to if we let the bottom of the ramp right here be our h equals 0, and we let the top of the ramp be h equal, what is that going to be, 3 meters to the top?
Yeah.
If we calculate the object's gravitational potential energy at the bottom, well, down here, PEG initial would be mgh. But what's the height going to be down there at the bottom? 0. So it would be mass of 10 kilograms times 10 meters per second squared times 0 meters, and we just get 0 joules. It doesn't have any stored up energy due to gravity down there at the bottom. If we calculate the gravitational potential energy at the top of the ramp, PEG final, that's going to equal mgh final. And this time, we get a value. The mass is going to be 10 kilograms, or a non-zero value, I should say, times 10 meters per second squared times 3 meters. And lo and behold, the potential energy due to gravity at the top of the ramp, 300 joules. So notice the change in the potential energy due to gravity, which is always final minus initial. Anytime you have a change, final minus initial would be 300 joules minus 0, positive 300 joules. What about the work done by the force due to gravity as the sucker went up? What was that? That was negative 300 joules. So we are going to swap out potential energy terms, but it's not just an even swap out. What's the hidden relationship between the work done by the force due to gravity and the change in gravitational potential energy? Work done by the force due to gravity equals the negative of the change in the potential energy due to gravity. This is an obscure formula which 9 times out of 10 we don't use, we don't think about. Normally, we're not going to calculate the work done by the force due to gravity. We're just going to calculate potential energy terms. But on the rare occasion that you're asked to calculate the work done by the force due to gravity, this is the relationship you need to know. It's the change in the gravitational potential energy. Almost. You just have to also negate it. So finally, we're ready to swap out the work done by the force due to gravity and replace it with these potential energy terms. I'm going to do a little bit of algebra. You're going to be razzle-dazzled, and then we're going to have our new and improved work energy theorem. Okay, so we left it off where kinetic energy initial plus the work done by conservative forces plus the work done by non-conservative forces equals the final kinetic energy. Now, there are other conservative forces. But for this syllabus, for this unit, the only conservative force we're going to be dealing with is the force due to gravity. So for now, the work done by the conservative force right here is simply going to be the work done by the force due to gravity. And what we're going to do is we're going to swap it out, and instead of calculating the work done by the force due to gravity, we're going to replace it with the negative change in gravitational potential energy. Now I'm going to run through some algebra steps. Feel free to copy it down, or feel free to just wait for the final formula, because it's like the new improved work energy theorem that you're going to learn to love. It's going to be like the go-to formula for this unit. Here we go. Initial kinetic energy plus the negative change in gravitational potential energy plus the non-conservative work. Instead of writing that whole word out, you can just write WNC equals the final kinetic energy. Another way of writing that change in potential energy, I could say initial kinetic energy plus the negative, there's my negative sign right there, the negative, well, change in potential energy, that's the final potential energy, PEGF, minus the initial potential energy. So in the parentheses, I have my change in potential energy plus any non-conservative work done kinetic energy. If I distribute that negative sign, like that, I get the initial kinetic energy plus the negative of the final kinetic potential energy, plus I have a negative sign here, then I'm distributing that negative sign, so I have the initial potential energy plus the non-conservative work equals the final kinetic energy. Last but not least, you see this final potential energy term? I'm going to take it over to the other side. There's an Aerosmith song. Take me to the other side. It's a good song. Look it up. When I do that, what am I left with? The final version of the work energy theorem.
Go back for 1 second.
Sure. Ready, Freddie? The initial kinetic energy plus the initial gravitational potential energy plus any non-conservative work done equals the final kinetic energy plus the final gravitational potential energy. So if you add together the KE and the PEG to begin with, and you compare it to the KE plus PEG at the end, they're going to be equal if there's no non-conservative work. But if there is additional work done, like an applied force, pushing it to make it go faster, then this sum over here will be bigger. Or let's say there's only friction force going on. This would be negative. Well, then the sum of the KE plus the PE over on this side would be smaller. If there isn't any non-conservative work, they would be equal. So if we just hide that non-conservative work, let's say nothing comes from the outside and gives it a push, and there is no friction, then the total KE plus PEG to begin with would equal the KEF plus the PEGF at the end. This is called conservation of mechanical energy. These two terms together added up, the kinetic energy plus the gravitational potential energy, they're referred to as mechanical energy. So the initial mechanical energy would equal the final mechanical energy when there aren't any non-conservative forces doing work. When there isn't any applied force making the object going faster and faster, or when there isn't any friction force making it slower, slow down, then the two are equal to each other. Now, if there is non-conservative work, then we have to add that in right here. And sometimes that non-conservative work is positive, and sometimes it's negative. If W and C equals 0, then the mechanical energy initial equals the mechanical energy final. And anytime you have a quantity that stays the same here as it is there, it's referred to as a conservation of mechanical energy. But you only have conservation of mechanical energy when there isn't any non-conservative work done. Speaking of which, we went and we defined conservative work, but we never defined non-conservative work. So why don't we do that right now? It's simply the opposite of conservative work. Instead of not depending on the path taken, this time it does depend on the path taken. The path that you choose to take does affect the non-conservative work. An example of non-conservative work is the work done by the force of friction. The work done by the force of friction does depend on what path you take from the starting point to the ending point. Say, for example, you're looking at a book set on a table, bird's eye view. Here's the tabletop, looking down from above, bird's eye view, and over here we have a book. Now, if I drag that book and I just push the book across the table over to the other corner, as I drag it this way, I'd have to be putting an applied force on it, pushing it diagonally this way. The friction force, the rubbing between the bottom of the book and the table, would be acting in the opposite direction. And that rubbing force, work done by friction, generates heat. Now, instead of pushing the book directly there, if I took that book and I first moved it over here, and then I pushed it over here, and then I pushed it over here, and then I pushed it, and then I finally pushed it to there, all along that path, as I'm pushing the book, I would be fighting the friction force, which always acts in the opposite direction of the motion, guess how the work done by the friction force along this green path compares to when I directly went straight there, Liz?
It's greater than.
It's going to be way more. I'm going to have to do a lot more work against it because there's going to be a lot more rubbing. I'm going to generate a lot more heat. So the work done by the friction force does depend on the path taken. Another example of non-conservative work is when somebody comes from the outside and pushes on an object. Again, this depends on the path taken. So these types of works cannot be replaced by potential energy terms. If there is an applied force and if there is a friction force, we're going to have to calculate them the old-fashioned way. We're going to have to use the formula W equals F times X times cosine of theta, just like we did on that inclined plane problem. We're not going to be able to swap it out and replace it with easy MGH terms or anything like that. We're going to have to go back and use the good old-fashioned work equals force times X times cosine theta. And where will that fit in? Right there. That's where those works will fit in. Yes. Yep. So, if we really wanted to blow it out, we could write it like this. And this is how we're going to leave it here. The initial kinetic energy plus the initial gravitational potential energy plus the non-conservative work.
F times X cosine.
I'm not going to take it that far, but you're right. That's what you would have to do. I'm just going to say here the work done by any applied force plus the work done by any friction force. And those two together make up the non-conservative work equals the final kinetic energy plus the final potential energy due to gravity. Nine times out of 10, though, we're simply going to write KEI plus PEGI plus the non-conservative work, because that's what these two together are called, equals KEF plus PEGF. And you're going to learn to really like this formula. It actually is less scarier than it looks. Some people are like, oh my goodness, look at all those terms. But you're going to see how like a lot of things like will cancel out in certain circumstances, and you'll get very comfortable. And that's what we're going to do in class tomorrow, is we're just going to do sample problem over sample problem using the new and improved work energy theorem.